Okay, normal distribution, and notice brand new office. I've made my new home office with a very comfy mat and a stand-up desk. I know you were all worried about what I was doing, but now it's very comfy. So anyway, without any further ado, normal distribution. So this is the go-to for all statisticians is the normal. So we've got random variable y, and we're going to say it has a normal probability, and it has two parameters. First of all, sigma, which will always be greater than 0, and mu, which will lie between minus infinity and infinity. And we'll see later that these are measures of spread and location. And here we have our probability density function. So you've got this 1 over sigma square root of 2 pi e to the minus y minus mu all squared over 2 sigma squared. And we will denote this as y is normal with mu sigma squared. That's not always the case. You'll find that some textbooks will use sigma as the parameter that they use in the end, so it's always worthwhile checking which it is. Now, there's a standard one. We decided to have a single standard one, and the standard one is the one where we have an expected value of 0, so mu equals 0, and the variance and the standard deviation is 1. And that's what we call the standard normal. Why do we have a standard normal? Because you can't integrate this. You know, the idea is that you take your PDF and you integrate to get your probabilities. You can't analytically integrate this. You're going to have to do it numerically. And so before we had computers, we would have tables that we'd use to give the probabilities. And rather than having lots of tables, we just had a single standard table. And the whole idea would be that we would take our calculations, convert them to a standard, and then look it up on the standard distribution. So I'm just going to quickly cover that. The only time you're going to really need this is if you get sucked into a time vortex, you go back to 1950s, and for some reason when you arrive there, what you really want to do is a normal calculation. That is reasonably unlikely, but just in that case, let's make sure we can all do standardization. So the whole idea is that if I had a normal distribution with a mean of mu and a variance of sigma squared, and I want to work out the probability that y lies between A and B, what we do is we take A and we take off mu and divide by sigma, and we do the same for B. And now I can work out my probabilities by using a standard normal table. What we actually do when we do our standardization, we are calculating how many standard deviations away from the mean A is and how many standard deviations away from the mean B is. That is it. That's it. I'm not going to show you an example. I'm not going to go into details. We now have code, computers that can do all this, so I'm not going to bother. How do we do it? Well, again, if y is normal with a mean of mu and a variance of sigma squared, to do less than or equal, we do our p-norm. Notice the value that we put in is our standard deviation. We can do our simulation. I'm also going to give you another one, what we call an inverse CDF, which is Q-norm. And we'll use that in a second to calculate something. So let's have some examples. We've got a random variable that's normally distributed with a mean of 4 and a variance of 16. And we're going to calculate the probability that y lies between 0 and 8, the probability that the y is greater than or equal to 1, and we're going to find a value of a such that the probability y is less than or equal to a equals 0.25. So let's do this. So the first one. So let's just remind ourselves what we've got. We've got y is normal for 16. So we've got mu equals 4, sigma squared equals 16, so sigma equals 4. We want the probability that 0 is less than or equal to y, which is less than or equal to 8. Well, let's draw what we're looking at here. We've got our 4 here. So we basically want to go to about 8 and about 0, and we want this area here. So that is the probability that y is less than or equal to 8 minus the probability y is less than or equal to 0, because the area probability less than or equal to a is all this. And then I just take off this area here, and what I get left is what I want, just this bit here. So that is going to be p norm 844 minus p norm 044. When I put that into RStudio, I got 0.6827. What's the next one we want? We want the probability that y is greater than or equal to 1. So here's our 4, here's our 1. We want this area. We know the total area is 1. So if we just take off this area, we'll get what we want. So that's going to be 1 minus the probability y is less than or equal to 1, which equals 1 minus p norm 044, which is equal to 0.7734. This is such a common calculation we do where we want to do greater than. There's actually a quick way of doing it in R. Go and look at the notes, it shows you how you do that. Finally, what do we want? We want to find an A such that the probability that y is less or equal to A is 0.25. So we've got our distribution, here's our 4. We've got some A down here. We know that this area is 0.25, and I want to know what A is. So we call it an inverse CDF. The way you do it is A is equal to Q norm 0.25 44. You find that's 1.3020. So, why do we have these parameters? Well, the first thing is, if y is normally distributed with a mean of mu and a variance of sigma squared, we can show that the expected value of y is mu, the variance of y is sigma squared, and for completeness, the moment generating function is e to the mu t plus sigma squared t squared over 2. Well, I'm not going to prove all of these, but let's have a look at showing the expected value. So let's do the calculation. We want expected value of y is equal, well, we're going to integrate from minus infinity to infinity y, and now our probability mass function. We're going to have sigma the square root of 2 pi, and then we've got e to the minus y minus mu squared over 2 sigma squared dy. Well, we're going to simplify this a little bit. We're going to let z equal y minus mu on sigma. What does that mean? If we rearrange it, we get that y equals z sigma plus mu. So in our calculation, we have a y, we can replace that, but also we've got a dy, so we should replace that as well. So we'll look at dy over dz. So we'll differentiate that with respect, and that gives us sigma. What does that tell us? That dy is equal to sigma dz. The third thing we have to do is we have to change the endpoints of our integration, but that's not a problem. If y equals infinity, infinity minus mu over sigma is still infinity. And if y equals minus infinity, then z is still minus infinity. So putting that all together, our new integration goes from minus infinity to infinity. We've got z sigma plus mu over sigma 2 pi. E to the minus, you substitute in, you'll get z squared sigma squared on 2 sigma squared, and then the dy replaced with a sigma dz. Those cancel, and we can now actually split this into two parts. We've got an integral here which is z sigma on 2 pi square root e to the minus z squared on 2 dz plus mu over 2 pi sigma squared e to the minus z squared on 2 dz. Well, what do we notice? Well, first of all, this mu can come out the front. And what have we got? We've got the integral from minus infinity to infinity 1 over 2 pi square root e to the minus z squared over 2 dz. Well, the first time we see Gary-Glonick trick 3, which is times by the integral over a PDF. What's our PDF? Well, you recognise that as the PDF of a standard normal, and we're integrating on it, so we get 1. So this whole first term just becomes mu. What about this second term? We've got sigma we could bring out the front, and now we've got z e to the minus z squared over 2. Well, it's going to be complicated, but go and draw it in a graph. You'll find it looks something like that. It's actually what we call an odd function. Basically, this bit is like the flip of this bit. And because we define the areas underneath this line are negative, and these are the same things, these two areas are equivalent, it wipes it out, so this whole thing is 0. So finally our expectation is mu. So there we are, our first ever Gary-Glonick trick number 3. That's the end of lecture 14. In the next lecture, we'll start looking at the exponential and the gamma distribution. Thank you very much.